Hello everyone.
దాంట్లో దీన్ని యూస్ చేస్తాను చూడండి ఇలా సో దట్ అది సౌండ్ వచ్చలేదు.
Hello everyone. Let us discuss matrices and determinants chapter 1.1. First coming to the definition of a matrix. An ordered rectangular array of elements is called a matrix, or you can define in another way, a set of mn numbers arranged in the form of rectangular array of m rows, each row consisting of an ordered set of n numbers, is called an m by n matrix. M by n is also called as order of the matrix. Suppose a matrix of order 3 by 2. You can say it contains of 3 rows and 2 columns. So we can write for an example 3 by 2 matrix. Yeah, you can see which contains 3 rows and 2 columns. So 3 by 2 is called as order of the matrix. Now, in general, a matrix of order m by n can be written as A is equals to Aij of m by n, where I ranges from 1 to m and j ranges from 1 to n. Let us discuss about types of matrices, in which first we can discuss about a row matrix. A matrix having only one row is called a row matrix. So columns can be of any number. You can look at an example. A is equals to a matrix containing one row, 4 columns there are. So as we discussed, the definition says a matrix which contain one row is called a row matrix. So columns can be of any number. So we can take one more example. A matrix containing one row but 5 columns. So this also called a row matrix. Coming to the next type, column matrix. A matrix having only one column is called a column matrix. As we discussed earlier, a row matrix similar to that matrix contain one column is called a column matrix. So rows can be of any number. So you can observe this example which contains one column, 3 rows. So 3 by 1 is the order. So column is 1. So it is called as a column matrix. You can see one more example. A is equals to matrix containing one column 1 3 5 7. Rows are 4. So its order is 4 by 1. Next coming to a null matrix. A matrix in which each element is equals to 0 is called a null matrix. That means whatever the elements present in that matrix should be zeros. So whether the order is of 2 by 2 or 3 by 3 or 3 by 2, any. So you can see this example. This is the matrix which contain all zeros of order 2 by 2. So it is called a null matrix of order 2 by 2. Null matrix in general we denote with the letter O of order 2 by 2. So we mention the order as a suffix of O. You can look at this example. So this is a null matrix of order 3 by 3. You can take as 3 by 1 also, a matrix containing 3 rows and 1 column in which all the elements are zeros is called a null matrix. Next coming to diagonal matrix. A matrix A equals to Aij of n by n is said to be a diagonal matrix if Aij equals to 0 for all I not equals to j. Students, just remember a matrix A is equals to Aij of order m by n. Of order 3 by 3. You can write as A11, A12, A13, A21, A22, A23, A31, A32, A33. You can observe one thing. This is the first row, so the row number in all these elements, 1 I kept, and this is the first column, so the column number in all these I kept 1. So the first number denotes the row number and next number denotes the column number. So based on, suppose you can see A32, it is an element which contains in third row second place. So you can identify its position, third row second place. So this is the element A32 means. So based on this we can define a diagonal matrix in which aij equals to 0 for I not equals to j. You can observe one thing, this is said to be the principal diagonal in which I and j both having the same number. So I equals to j, you can observe here. The remaining elements, all these three having I not equals to j, and not only those three, these three also satisfying that property I not equals to j. So based on the definition, the elements where I not equals to j must be zeros. So other than the principal diagonal, all the other elements should be zeros. That way you can remember. So a diagonal matrix we can define as a matrix A equals to aij of n by n is said to be a diagonal matrix if aij equals to 0 for all I not equals to j. You can look at an example here. Diagonal contains zeros or non-zeros, but the non-diagonal elements, so the elements which are not in the diagonal, must be zeros based on the definition. Next, coming to scalar matrix, a matrix A equals to aij. Next coming to scalar matrix, a matrix A equals to aij of n by n is said to be a scalar matrix if aij equals to 0 for all I not equals to j and aij equals to some scalar k for all I equals to j. So as we discussed earlier, A is equals to a matrix of order 3 by 3 can be written as A11, A12, A13, A21, A22, A323 and A31, A32, A33, in which I not equals to j means these are the elements which satisfy that property, so these three should be zeros, and the other elements where I equals to j, so these are the elements which are in the principal diagonal satisfying the property I equals to j, so those should be some k. So a scalar matrix must be in this form. So a matrix which is in the form k0 0 0 k0 0 0 k is said to be a scalar matrix where k can be any real number. You can look at an example. A matrix A is equals to 300 030 003 is called as a scalar matrix. Next, coming to identity matrix, which is one very much important. A matrix A equals to aij of n by n is said to be an identity matrix if aij equals to 0 for all I not equals to j and aij equals to 1 for all I equals to j. So as we discussed in the previous definitions, their positions, so we can write directly the elements which satisfy I not equals to j property must be filled with zeros, and the elements which satisfy the property here I equals to j must be filled with 1. So we get this matrix. Identity matrix we denote with the letter I. Since it is of order 3 by 3 which I wrote here, so I3 we denote it as. Similar way we can say I2 also. So identity matrix of order 2 by 2 which can be written as 1 0 0 1. Identity matrix of order 1 by 1 also we can consider as only 1. You can look at an example of order 3 by 3. So it is identity matrix of order 3 by 3. So we can denote it as I3. Next, control. Next, discussing about an upper triangular matrix. A matrix A equals to aij of n by n is said to be an upper triangular matrix if aij equals to 0 for all I greater than 0. So,
I greater than 0.
Consider an example, a matrix containing matrix of order 3 by 3. The elements which satisfy the property I greater than j. So you can look at these elements in which I is greater than j. So these three elements, if they're zeros, then you can call such matrix as an upper triangular matrix. You can see an example, in which these three elements are zeros. So it is called an upper triangular matrix. Next, coming to lower triangular matrix, matrix A equals to Aij of n by n is said to be a lower triangular matrix if Aij equals 0 for all I less than j. So as opposite to the upper triangular matrix, the elements which satisfy the property these are the elements which satisfy the property I less than j, so these three must be 0. So you can look at the example. These are the elements which satisfy the property I less than j, so it is called a lower triangular matrix. Next topic, trace of a matrix. It is defined as the sum of elements of the principal diagonal of a square matrix is called a trace of a matrix. It is denoted by TR of A. Suppose a matrix A is equals to of order 3 by 3, let us consider 1 2 3 4 5 6 7 8 9, which is of order 3 by 3. So this is the principal diagonal. So the sum of elements of the principal diagonal, so 1 plus 5 plus 9 is called as trace of the matrix A. So it is denoted by TR of A, which gives to 15. So trace of the matrix A of this example is 15. So trace of the matrix you can denote like this: trace of a matrix A is equals to sigma I equals to 1 to n of AII. Let us see some few properties related to trace of a matrix. Trace of A plus B is same as trace of A plus trace of B, and trace of A minus B is same as trace of A minus trace of B. Next, trace of AB is same as trace of BA. Trace of KA, where K is any scalar, is same as K into trace of A. Next, let us discuss about addition of matrices. Addition of matrices is possible if the matrices are of same order. You can look at the matrix A equals to Aij of order m by n and B equals to Bij of m by n. You can see the orders of both the matrices which are same. So matrix addition is possible. So the matrix A plus B can be written as Aij plus Bij, which is of same order m by n. So if you consider an example, matrix A is of order 2 by 2 and B is of order same 2 by 2, then A plus B can be written by the definition 1 plus 1, 2 plus minus 1, 3 plus 2, 4 plus 3, which gives 2, 1, 5 and 7, which is of order again 2 by 2. So we can conclude one thing: addition of matrices is possible if the orders of both the matrices are same. Let us see properties of addition of matrices. First, matrix addition is commutative. So A plus B, B plus A are equal, and matrix addition is associative. A plus B plus C is equals to A plus B plus C. Matrix addition is associative, that is A plus B plus C is same as A plus B plus C. Next, existence of additive identity. A plus matrix 0 matrix is same as 0 matrix plus A is equals to A. So this 0 matrix is called the identity matrix with respect to addition. Existence of additive inverse. A plus minus A equals to minus A plus A equals to a 0 matrix, then you can call minus A is the additive inverse of the matrix A. So if you take a matrix, for example, of order 2 by 2, matrix A is equals to of order 2 by 2, here let us consider 1 2 3 4, then its additive inverse can be written as minus A, which is minus 1, minus 2, minus 3, minus 4, which is also of same order 2 by 2. So minus A is called the additive inverse of the matrix A. Next, cancellation loss holds good in case of addition of matrices. First, you can see the left cancellation law. If A plus B equals to A plus C, then we can write B is equals to C, which is called as the left cancellation law, and B plus A equals to C plus A, which you can write again as B equals to C, which is called as right cancellation law. Few more properties related to addition of matrices. If A and B are any two matrices of same type, which means of same order, and alpha beta are any two real numbers, then alpha into A plus B equals to alpha A plus alpha B, alpha plus beta into A equals to alpha A plus beta A, alpha into beta A is equals to alpha beta into A. That's all. Next topic, multiplication of matrices, which is very much important. Multiplication of matrices AB is possible if number of columns of the matrix A is equals to number of rows of the matrix B. Let us consider an example. A is a matrix of order 3 by 2 and B is a matrix of order 2 by 1. Is multiplication possible? Means yes. Number of columns in the matrix A and number of rows in the matrix B, both these are same. So multiplication is possible, and the matrix which you get after multiplication will be of order 3 by 1. So properties of multiplication of matrices. Let us take A, B, C, 3 matrices where multiplication is defined. So first property, matrix multiplication is associative, which is AB into C equals to A into BC, and distributive property A into B plus C equals to AB plus AC, which you can call in particular left distributive property. And next, right distributive property A plus B into C equals to AC plus BC. And fourth, very important, matrix multiplication is not commutative. So AB not equals to BA. And the last one, AI equals to IA equals to A means then you will call I and multiplicative identity. Thank you.